everyone, I'm Xinhua. We present Augnlg few-shot natural language generation using self-trained data augmentation. This work focuses on the few-shot natural language generation. We introduce Augnlg, a novel data augmentation approach that combines the self-trained neural retrieval model with the few-shot learned NLU model to create MRT text data from unlabeled open-domain texts. Augnlg is fully automatic without needing any actual labeled MRT text data. It mostly outperforms the state-of-the-art method on existing few-shot NLG data in both surface-level similarity metrics, for example BLEU, and semantic correctness metrics, for example slot error rate. Since our approach is independent to existing transfer learning approaches, it can be used in conjunction with other approaches. Other than the novel introduced architecture, we propose and test our approach on a new few-shot learning testbed, few-shot SGD. We also provide comprehensive analysis results on the key components of our system to gain detailed insight into the relationship between the component-wise behavior and the various parameters. NLG is the key component in the task-oriented dialogue system, which converts the structured meaning representations to the natural language. For large-scale conversational systems, where it is common to have over hundreds of intents and thousands of slots, it is important for an NLG system to generalize well with limited labeled data in real applications. In the few-shot learning setup, the number of training examples is extremely small, which easily leads to non-fluent generation with many grammar mistakes and hallucinating or missing pieces of information. For example, in the first case, the text misgenerated the name of the restaurant. In the second case, the generation forgot the slot is for business and its value. In the third case, the phrase, "the park is north," is not fluent. In order to tackle the data sparseness problem, we introduced a three-step pipeline to gradually involve a general large-scale language model to the domain-specific NLG model. Firstly, we pre-train a base language model with massive amount of plain text. In this work, we directly adopt the pre-trained GPT-2 model as the base language model. GPT-2 has demonstrated a remarkable performance on autoregressive text generation tasks, which is close to MRT text generation. However, GPT-2 is pre-trained on open web text, so the language style and topic is quite different from those of daily conversations in target domain. Also, the generation task in NLG is conditioned on the input MR, while GPT-2 pre-training tasks are unconditioned generation. To bring the model a step closer to the final NLG model in the target domain, we continuously pre-train the model on automatically augmented MRT text pairs. Finally, we fine-tune the NLG model on a limited amount of in-domain few-shot MRT text pairs for the final adaptation. Our main contribution is the NLG-specific continued pre-training. Previous work achieved a state-of-the-art performance in the few-shot NLG settings by using existing MRT text dataset in the task-specific continued pre-training. However, this approach leaves little room for further improvements as MRT text data are expensive to obtain for new domains. So practically, it circles back to the same scalability problem after exhausting the existing data. In order to go beyond this restriction, Augnlg creates MRT text data from unlabeled open domain texts. Since Reddit has shown to provide natural conversational English data, we adopt Reddit as the open domain utterance pool. The data augmentation procedure aims to construct a larger amount of MRT text pairs from open domain texts that can relevant to few-shot in-domain MRT text pairs. The augmentation process consists of two stages. First, retrieve the keyword matching utterances and filter out the domain irrelevant instances, and then generate synthetic MR annotations. The utterance retrieval and filtering procedure consists of three steps: keyword extraction, keyword-based retrieval, and self-trained filtering. Keyword extraction aims at collecting n-gram keywords from the in-domain utterances. We first gather all the n-gram phrases that appear in the utterances and then filter out those n-grams with relatively low TF-IDF scores. Having the extract keywords, we retrieve utterances from the open domain utterance pool that contains at least one extracted keyword in it. The aim is to source a larger amount of domain-relevant candidate utterances based on the surface level overlap. The retrieved utterances can be quite noisy. For example, the utterance with kids movies was retrieved by the background with kids from the restaurant domain. However, the utterance is about movie instead of restaurant. So we introduced the self-trained BERT-based classifier to filter out irrelevant utterances from the retrieved candidates. At each iteration in the self-training, we make predictions on the retrieved candidates. The utterance with highest score together with the few shot in-domain utterances are taken as positive examples, while the rest utterances are taken as the negative examples for the next iteration of self-training. Once the training loop gets converged, we label all the retrieved candidates with the classifier from the last iteration. Then we build the final augmented utterances by filtering out the ones with lower classification scores. After getting the domain-relevant utterances, we label a synthetic MR to each of them using a few-shot natural language understanding model trained with the in-domain data. The outcome is the complete MR to text augmentation. To evaluate the contribution of the augmented data to the few-shot analogy task, we apply Augnlg to two baselines. First, FT-GPT, which directly fine-tunes the GPT-2 on the in-domain few-shot MR to text pairs. We introduce Augnlg FT, which further pre-trains the GPT-2 on the augmented MR to text pairs and performs the final fine-tuning on the in-domain data. We evaluate the model generation using BLUE. As we can see in these two tables, Augnlg FT substantially outperforms FT-GPT across all domains on both few-shot WALD and few-shot SGD datasets. We also evaluate the semantic alignment in terms of slot value insertion and omission using slot error rate. The table shows that Augnlg FT managed to outperform FT-GPT by a large margin. Then we apply Augnlg to a stronger baseline, SCGPT, which further pre-trained the GPT-2 on existing MR-to-text data borrowed from other NLG corpora before fine-tuning on the in-domain data. We introduced Augnlg SC, which pre-trained GPT-2 on both existing MR-to-text data and automatically augmented data, and finally fine-tuned on in-domain pairs. The two tables show that Augnlg SC performs better than SCGPT and achieved the state-of-the-art performance in most domains in both BLUE and slot error rates. To understand the quality of the augmented data, we introduced 4 metrics for the direct evaluation on the augmented data. MR coverage evaluates the coverage of the lexicalized MR of the test set in the augmented set. Slot coverage evaluates the coverage of the slot keys of the test set in the augmented set. Language model perplexity is the perplexity of the augmented utterances calculated by a GPT-2 language model fine-tuned on the test set. Lower perplexity values indicate that the distribution of augmented utterances is close to the distribution of the test utterances. N-gram novelty measures the fractions of the n-grams in the test set that do not appear in the augmented set. The experiment results shows that the slot coverage achieved 70% in most domains on both few-shot WALD and few-shot SGD datasets, while MR coverage has the wide range of value across domains. The MR coverage results strongly correlated with the performance of Augnlg FT on few-shot SGD datasets. We compared the augmented data with the existing MR-to-text data from other corpora in language model perplexity and n-gram novelty. Augmented data achieves lower perplexity and n-gram novelty in all domains compared to the existing MR-to-text data. We also found that there is a general proportional relationship between the performance of NLU and NLG. Lastly, we found that the effectiveness of Augnlg culminates at the smallest training set and gradually diminished as the training data become available. Thanks for watching.